Welcome to the next video in the Real Analysis video series, and in this video we are going to look at the solution to that previous exercise. So we're going to prove that every finite set has a max and a min. I'm going to do this by induction. So just to be explicit about how this induction works, let's define a property of a natural number I. So this is phi of I. By the way, if you're not familiar with proof by induction, then there is a video in the Real Analysis video series which discusses this somewhat at length. And so I haven't made that video yet, so I can't link it in the description to this video. So if you're watching this video and you wish you had that link, then maybe leave a comment below to remind me to link it up, and if I have the time, I will go look for it and supply the link. Okay. But in any case, for now, I'm just going to assume that everybody knows how to do a proof by induction. Okay, so we're going to be very explicit about the property that we're going to prove for any natural number I. So what we're going to say, right, like phi of I says any set of I elements has a minimum. And so I guess, yeah, here I seem to, okay, so I guess I chose to prove that the set X has a minimum. And as I like to often do, if you've got this kind of duality of a minimum and a maximum, I like to typically just show you the proof for one of them and then let you do the proof for the other one, because it goes almost the same way, and maybe it's a nice exercise for you to do, to have something that is very, very similar, but only slightly different. So anyway, point being, I am going to prove that any finite set has a minimum, and I'll leave it to you to prove that any finite set has a maximum. But okay, so that's what we're doing here. Oh yeah, and this explicitly says non-empty finite set, and my induction is going to start for I equal to 1. Okay. So the base case I equal to 1 is clear. So, but although it is clear, we should really expand on exactly what's going on here. Just as good proof habit to just say things as explicitly as possible. So, suppose that X is a set of just one element, and we're going to prove that it has a minimum. So if it has just one element, then we can name that element. So let's say that X is the set of just the element little x. Now we need to prove, right? Like, what does it mean? I'm going to claim that this little x is the minimum of the set, which I think is obvious, but technically what does that mean? Technically that means, by definition, that for every element in our set, the thing that I claim is a minimum, this one, is less than or equal to every element of the set. In this case, every element of the set is just the same little x that we've been talking about this whole time. So anyway, we need to prove that this is true for, really, there's just one element. So we just need to show that this is true. And that's really trivial, of course, because the ordering relation is an ordering relation, and therefore it is reflexive. And so this must be true, and that effectively ends the proof of the base case. Okay, so we've now shown that every set of just one element has a minimum. Okay, so the property phi is satisfied when I is equal to 1. Now for the inductive case. So we assume, for induction, that the claim is true if you have a set of size n, and we will use this fact to show that it is also true for any set of size n plus 1. So let's say that X is a set of size n plus 1. Well, since it has size n plus 1, it cannot possibly be non-empty, right? Of course, n, the least that we would let n be is 1 in this proof by induction, 0 for this proof by induction. But in any case, the important point is that if it has size n plus 1, then or sorry, no, the least that we would let n be is 1. That's the starting point for this particular induction. So again, anyway, the important point is that it is non-empty and we can select an element out of the set, right? So since it has size, x has size n plus 1 and n is at least 1, then there is at least one element in the set and we can choose it, right? We can talk about it. We can pick an element out of the set. So that's this step. Now consider the set Y, which is constructed by removing little x from big X, right? So we've just reduced its size, right? We've now, Y is now a set with one fewer element and therefore has size n, and therefore the inductive assumption applies to Y. This just tells us that Y has a minimum, which we can call alpha. So alpha is the minimum of Y, and now we want to somehow find the minimum of X from all of these components. And it'll be somewhat importantly different depending on whether alpha is less than or equal to X or X is less than alpha. And these are the only two possibilities, by the way. It is possible to prove that precisely one of these must hold, but that's probably not a hard proof, and so maybe if you're interested, you could go ahead and prove it for yourself. But it is possible to prove that for any two real numbers, precisely one of these two must hold. We're going to use that fact in our proof to do a proof by cases. So we'll consider the former case in which I claim that alpha is then a lower bound on all of X. We know that it's already a lower bound on Y, and Y is, in a sense, kind of most of X, right? If you pick any element out of X, basically there's just two possibilities. Either it is this little x or it is not, okay? Let's just say for all Y in... Sorry, I shouldn't say Y because that gets confusing with big Y. So let's say maybe Z. So let's say for all Z in big X, if Z equals X, then alpha less than or equal to Z, because of what we already, right, like because of this assumption that alpha is less than or equal to X. So that's one case. And otherwise, Z is an element of Y because Y is everything in X other than little x. So that puts, right, so if this equality does not hold, then that immediately gets us that Z is in Y. And then we get that alpha is less than or equal to Z, but this time it's because Y is the minimum, alpha is the minimum of Y. So anyway, the point being that for all Z in X, alpha is less than or equal to Z, making alpha the minimum of X. And by the way, we also, maybe I should also remark that we know that alpha is in X because it is the minimum of Y, therefore it is in Y, therefore it is in X. So there you have it, right? So that's the sort of argument that in the former case, alpha is the minimum of X. Okay, now let's talk about the latter case. Here, where X is strictly less than alpha, I now claim that little x is the minimum of big X. So how could we possibly see that? Well, and by the way, we know that little x is in big X, so that's part of being a minimum, and we already have that. So let's now consider for any Z, and by the way, this is in the latter case, right? In latter, for any Z in the set X, if Z equals X, then trivially by reflexivity, X less than or equal to X, or let's say X less than or equal to Z, to make that a little more explicit. Anyway, otherwise, right? Otherwise, Z is in Y, and we get that X is strictly less than alpha, but alpha, being a lower bound on Y, is less than or equal to z, and then by the sort of transitivity and so on, right? This is another thing that I'm going to do, which you could prove, and it's a good exercise to prove it, but I'm just going to use it. From here, we could then say that x is less than or equal to z. And the important sort of upshot of all of this is that now x is the minimum of big X. So what we have shown is that no matter which of these two cases you have, X must have a minimum. So that concludes the inductive case and therefore concludes the proof by induction. That then means that for each natural number n where n starts at 1, then any set of size n has a minimum, and that shows that if X is finite and non-empty, then X has a minimum. And then the proof that every finite set has a maximum, you could repeat if you wanted to do it that way, and simply prove maximum facts rather than minimum facts, and otherwise the proof would be almost the same. Okay. Next exercise is to show that if a set has a maximum, and of course, right, this would hold just as well for a minimum, but I'm just going to state it for a maximum. If a set has a maximum, then that maximum is unique. And so I'll reveal my solution in the next video.